This video lecture is about how stars are put together and how they shine.
Let's start with the first lecture slide. Much of what is known about the stars comes from studying the star closest to us, the Sun. At a distance of almost 150 million kilometers, the Sun is a few 100,000 times closer to us than the next nearest star. Because of its proximity, astronomers are able to study our star in much, much greater detail than they can the other stars. The Sun is by far the biggest thing in the solar system. Next slide. From its angular size of about half a degree and its distance of almost 150 million kilometers, its diameter is determined to be about 1.4 million kilometers. That's 109 Earth diameters and about 10 Jupiter diameters. All of the planets orbit the Sun because of its enormous gravity. It has about 333,000 times the Earth's mass and is over 1,000 times as massive as Jupiter. It has so much mass that it is able to produce its own light. This feature is what distinguishes stars from planets. Next slide. The Sun is entirely hot gas all the way to the center. This cutaway view of the Sun shows the four basic parts of the interior, from the core to the photosphere surface. It also shows the parts of the Sun's atmosphere, which we'll get to later in this lecture. The core is 16 million Kelvin, about 29 million degrees Fahrenheit, and it has a density 20 times greater than iron, but it is still gaseous because it is so darn hot. The energy from nuclear fusion is generated in the core, which makes up the innermost 10% of the Sun's mass. The energy then percolates outward through the radiative zone, which makes up about 85% of the Sun's interior. While the photons bounce around, moving energy slowly outward, the photons lose energy to the gas. Eventually, the photons, which started out as gamma rays in the core, have much longer wavelengths by the time they get to the outer 15% of the Sun's radius. The photons are more effectively blocked by the gas, so nature kicks in convection to carry the energy outward to the surface the rest of the way. The photosphere, which means light sphere, is the part we can directly see because that is where the photons finally escape to space. It is only about 500 kilometers thick, but on the scale of a 1.4 million diameter star, that photosphere is razor thin. The Sun's photosphere is about 5,840 Kelvin. Next slide. The photosphere has places where it is slightly cooler. These are the sunspots. Next slide. The sunspots are cooler areas of the photosphere, 1,000 to 1,500 Kelvin cooler. So they produce less light than the surrounding areas and look relatively darker. If you took a piece of sunspot away from the rest of the surface, it would glow a bright orange. This picture shows a group of sunspots and the fine-scale bubbling convection called granulation at the surface. I have a link to an old time-lapse movie of the convecting gas that makes the granulation, and then a link to the Daniel K. Inouye Solar Telescope's first flight images and movies released in January 2020. DKIST is on the summit of Haleakala, Maui, in Hawaii, and it will produce the highest resolution images of the Sun of any solar telescope so far. The images and movies are fantastic. Some sunspots last long enough to map the rotation of the Sun. At the equator, the sunspots take about 25 days to circle the Sun, but at the poles they can take a full month. The Sun is a big gas ball, so it does not spin as a single unit. Sunspots are regions of very strong magnetic fields. We know this by taking the spectrum of the sunspots, and we see that the absorption lines are split up into multiple components in what's known as the Zeeman effect. The strength of the magnetic field can be measured from the amount of separation of the components. Sunspots are associated with solar activity because all of the activity is caused by changes in the Sun's magnetic field. We see an increased amount of activity when the number of sunspots is high, and less activity when the sunspot number is low. The Sun's up and down cycle of activity varies with a period of an average of 11 years. Let's take a look at the current sunspot cycle plot page and scroll down to the plot of the monthly average sunspot number since 1750. This page is curated by retired NASA scientists Dr. David Hathaway and Dr. Lisa Upton. Next slide. This slide deals with various eruptions from the sun, such as prominences, which are cooled gas trapped in magnetic field loops between sunspots. The smallest one shown here is about 3 times the size of Earth. Flares are brief, very powerful eruptions lasting several minutes to a few hours when a magnetic field loop breaks. Usually a solar flare will also buffet gas trapped in the magnetic field of the corona, causing that trapped gas to burst free in what's called a coronal mass ejection, or CME for short. That then sends large amounts of charged particles out into the solar system at over 1,000,000 miles an hour. If the flare and/or CME is directed towards Earth, the ionized gas will cause radio interference and sometimes power outages and maybe even damage satellites. Our weather agency, NOAA, is tasked with monitoring this space weather because of the significant economic and geopolitical impact a bad flare or CME could have. This picture shows the connection between sunspots, prominences, and flares. Sunspots form where twisted magnetic field lines rise out of the photosphere and then loop back down into the photosphere and deeper layers. The magnetic field lines suppress the convection at those points on the photosphere, so energy has a hard time leaking out at those points on the photosphere. They are cooler than the rest of the photosphere. Gas in the chromosphere can be trapped to flow along the magnetic field loops to make the prominences, and if the magnetic field lines get so twisted that they snap, you can get a flare and usually also a CME. Next slide. I've already mentioned a couple of things in the sun's atmosphere. The chromosphere is the bottom part of the atmosphere right above the photosphere. Surprisingly, it is hotter than the photosphere and it has a very low density, so we can see emission lines. The emission lines are mostly from hydrogen, so the chromosphere has a bright red color. The corona is the sun's outer atmosphere. It is much hotter than the chromosphere at 1 to 4 million Kelvin, but it is very rarefied or tenuous, so there isn't that much heat content. The corona is the pearly white color surrounding the new moon during a total solar eclipse. Corona means crown because it looks like the moon is wearing a shiny crown during the total solar eclipse. In the X-ray and extreme ultraviolet wavelength bands, you can see more detail in the magnetic structure of the corona. The ions in the outermost part of the corona escape the sun traveling at 1,000,000 miles per hour and fill the solar system out to about twice the distance of Pluto in what's called the solar wind.